talk is going to be about effect of particle shape on the elastic anisotropy of granular materials. Now we all know that granular materials are very adaptive in nature. For instance, if you hold sand in your hand, it feels like a really loose materials, but we are also aware how to densify the same material and use it for different purposes, uh, ranging from energy absorption applications to all the way from road construction activities. However, by doing this, we are only harnessing a limited capability of these materials, which is the densification adaptivity. But these material also possess significant adaptive capabilities when it comes to varying the size, shape, and arrangement of the particles, and which has not been harnessed yet. For instance, if you look at these simple uniaxial compression experiments from Few et al., you can see that by varying the size of the steel balls, he basically is getting different response in the force and strain plot. Uh, so an important question arises is how can we harness this adaptive capability of these materials? Well, we need two main things. Number one is we need to determine the key important microscopic features such as the size, shape of these particles and their contact behavior. Number two is we need some smart constitutive models that can account for these microscopic features and predict the response of these materials. We can do that by using some simple second order continuum tensors, which are generally referred to as granular fabric and some internal variables. Uh, these models should also be able to work in the opposite direction, meaning if you want a particular response from these materials, you should be able to, they should be able to predict the required microstructure. That will be the ultimate goal of these materials, and that will lead us to harness the adaptive capability. However, to go there, we first need to develop and combine develop the constitutive model which can incorporate these features. And that is exactly what my research is based on. In the today's talk, I'll be talking more specifically about the elasticity that exists within the granular materials. Granular materials so far have been modeled using frictional plasticity models, rotational hardening models, but very few people have spent some time on understanding the elastic properties of these materials. And there lies a significant potential in elasticity in terms of elastic stiffness adaptivity. What do I mean by that? Well, if you look at the experimental results in this case, for the case of triaxial compression, here you can see that the stiffness ratio, the Young's modulus ratio obtained by dynamic measurements in the two orthogonal directions, you can see that the stiffness anisotropy is basically increasing as the stress state becomes more anisotropic, and this is true for all the sand types. Although some sands possess some inherent anisotropy, but the qualitative trend of this stiffness anisotropy remains pretty much the same. Why is that the case? That is what the goal of today's talk is going to be about, is to demonstrate how elastic stiffness anisotropy adapts based on the contact network and shape of the particles and develop constitutive models for the same. So to do that, the very first thing that we did is we basically relied on the DEM, discrete element method, and we prepared a granular assembly of spherical particles and we subjected it to isotropic compression. At reaching a 300 kPa confining, what we did was we basically inhibited all the inelastic sources of plasticity, meaning there is no frictional sliding allowed, there is no particle rotation allowed. So this assembly that you're seeing here is basically now an elastic assembly. And then we performed the simple elastic perturbations in the three orthogonal directions to determine the corresponding Young's moduli. The very first thing that we realized is that if you used, we basically used two different contact models, linear contact model and non-linear contact model. And the very first thing that we realized is that if you use the only way to get the adaptive elastic anisotropy is to use Hertzian contact model, which means that this elastic anisotropy arises due to the contact scale nonlinearity of the particles. And if we compare these results with the experimental results that I showed you previously in the last slide, you can see that even though we did not allow the particles to rearrange, but still the elastic stiffness anisotropy that arises due to the just the contact model itself, or the contact nonlinearity itself, accounts for more than 50% of the stiffness anisotropy shown in the experimental evidence, which is a big deal. Next thing we did was we wanted to understand if there is a corresponding microscopic feature that we can use to characterize this stiffness anisotropy. And for that, we use two of them: strong contact fabric and contact area fabric. Contact area fabric is something new that we defined and is based on definition of Hertzian contact law. And the difference between these two are essentially that in the strong contact fabric, you use averaging an average normal contact force, whereas you do not do anything like that in the contact area fabric. So that's a huge advantage. Next thing that we did was we basically used simple anisotropic elastic models, which are um, which are already derived in the Holsby's paper, 2019 paper, and they use a second order continuum fabric tensor. And then we use this model and two different potential functions for linear elasticity and non-linear elasticity, and calibrated this model against the DEM data that I showed you previously. And we realized that this fabric basically needs to evolve even in the case of elasticity. And we proposed a very simple evolution laws for this fabric, and therefore our stiffness now is also will also evolve as this fabric evolves, and basically the stiffness becomes more and more anisotropic. But how does all of this change when we incorporate the shape? In order to incorporate the shape, we used ellipsoidal particles in DEM, and we model it using the clumped particles to make sure that we are not doing any this clumping of the particles does not give any unreasonable or unrealistic response. We compared it against the analytical solution for the Hertzian contact for ellipsoidal particles, and you can see that even though quantitatively the trends do not exactly match, qualitatively uh, the trends predicted by the DEM clumps are pretty much very close to the analytical solution. Then we obtained and then we derived a simple expression for the modulus ratio of one single ellipsoidal particle, which is characterized by alpha aspect ratio. And we obtained a simple expression between the modulus stiffness ratio and the contact area fabric and the shape fabric. And here you can see the real difference or real effect of this contact area fabric, which would not have been the case for the strong contact fabric here. And we further used Oda's definition of shape fabric to enhance this definition and make it more general, that is for any orientation and any aspect ratio. And then we compared it for a regular crystalline packing for three different aspect ratios. And you can see that the expression basically performs really well. And then we compared this expression for the random packing as well, for four different orientations and three different aspect ratios. And still in this case, even though you see some slight unmatching, but overall the match obtained for all these assemblies are pretty good and pretty close to the expression that we have obtained here. Now the question comes, how can we enrich the existing continuum model? To do that, we cannot use the same fabric definition that we have used before, and therefore we use the DEM scale, the expression that we derived before, and the previously used the expression for continuum continuum fabric for spherical particles. And we this is the expression that we proposed, where one term is basically the induced term, or a reflection of adaptation in the contact area. Another term is the inherent term, which comes due to the shape itself. And we use this new enhanced fabric definition in that framework that I showed you earlier. And these are the terms that we used. And here, I did was we calibrated against the model for the DEM results for theta equal to 0, and then we predicted it for theta equal to 90. And then we did the same thing here for three different aspect ratios, and you can see that the predictions here are fairly good. So all in all, there are three major conclusions. Number one is the stiffness adaptive dependency on the external stress is basically emerges primarily because of the contact nonlinearity, and it can be linked directly to the contact fabric. And we proposed a correlation between elastic anisotropy and microstructural shape fabric, which is applicable for ellipsoidal shapes. And finally, we proposed an elastic constitutive model, which can account for anisotropy due to both contact area as well as for shape. And finally, these are my all my references that I have used.